we're going to be doing problem 1392 from chapter 13. And like I said, we're going to continue doing some of these problems to just get a better grasp of, not just using the angular motion equations that we've been using in cylindrical coordinates, but also to get that practice with that psi angle. For those who are just tuning in, the psi angle is this one, and your book kind of covers it. It's the angle that the tangent line makes with the radial coordinate axis. Okay, so let's get started with this problem. So we have a forked rod, a smooth cylinder C, having a mass of 0.5 kilograms. So okay, we have mass of 0.5 kilograms. To move along the vertical, keyword here is vertical, so we will have to take into account the weight of this particle. So and then path R equals 0.5 theta. So just because they just give me that already, I know my first time derivative just kidding, derivative is 0.5 theta dot. Okay, and then my second time derivative is 0.5 theta double dot. Okay, and then if the angular position of the arm is theta, okay, so they give us theta in terms of time. So when we take a time derivative, we actually don't have to do the chain rule. We can just easily just do the first derivative of the first time derivative of this equation, and we should bring the 2 down. We have t, and then theta double dot is just 1. All right. Where t is in seconds. Determine the force of the rod. Determine the force of the rod on the cylinder and the normal force of the slot on the cylinder at the instant t equals 2 seconds. So at t equals 2. Okay. What else? This cylinder is in contact with only one edge of the rod and slot at any instant. So we know this is going counterclockwise. Okay, so which is telling me that the particle, right? If we look at this particle, it has a force. The forked rod is hitting it with there's a normal force in this direction, and I call this n theta because there's the normal force is directed on the theta axis. Okay, but then there's also this this other force that's being done by the by the slot itself, which is maybe it's going to be going something like this, something pointing down, and then we do have to take into account the weight. Okay, so if you're doing this problem and you forget the weight, you're doing it wrong. Okay, so this is W. Let's just draw this bigger. But before we do that, let's take the particle. Here we have a tangent line. I'm gonna draw it. I'm gonna draw it like this. This is the tangent line. It keeps glitching for some reason. Tangent line. Okay. And then I'm gonna have my coordinate system like this. This is theta, and this is the radial axis, R. Remember, R just always extends, it just kind of goes along towards the position of the particle. Okay, so that extends out. So what I want to do first is draw the forces that are going to be acting on this thing. I know my weight is, the weight will just always be vertical. Okay, so if I can draw a nice vertical line here. So this is my weight, mg. Okay, now let's look at the two forces that I drew here. The normal force done on the particle by the rod. That's the normal force. It's going to be directed along the theta direction. Okay, and then I have a normal force done on the particle which is perpendicular to the tangent line. Okay, so this is where it kind of gets a little confusing, just because if you don't draw, if you kind of do a sloppy drawing, everything might, this normal might fall in line with the weight, and then visually you're going to confuse yourself. Mathematically, you might not. Okay. So here we are. We have the three forces that are acting on the particle. Okay. Now we want to be able to distinguish what is this angle with the radial axis, right? The tangent with the radial axis. And to do that, we need to do the psi, or I guess tan psi is equal to r dr d theta. Okay. So what's r? Well, r is 0.5 theta. Okay. And then what is dr d theta? That's just 0.5. Okay, so this goes away, this goes away. Now we're left with psi is inverse tan of theta. Okay, and then let's evaluate it at, let's see, at t equals 2, theta is equal to, let's see, 4 times 0.5 is 2. Theta dot is 2. Theta double dot is 1. Okay, so when we evaluate this, we should get psi is equal to, let's see, plug that into your calculator, we should get 63.4 degrees. Okay, so here's psi. Okay, alright, that's good. Where are we here? Let me get my calculator. So 90 minus psi, 63.4. That'll give, oops, so control Z that. Let's switch to purple. So now this angle here in purple, look at the bottom left. That's going to be phi equals 26.6. All it is 90 minus psi, right? Because we're just trying to determine what the angle between the tangent and the theta axis is. Okay, and we have that. And then if you went through the last problem I did, which was 1389, we know that this angle here is the same thing. It's going to be psi. Okay, so now I can break this normal into its radial component and the angular component. Alright, which is important. Another thing we're going to have to do is, let's see, break the weight down into its angular and radial component. So that's the tricky part of this problem. So you think you're done here, but no, don't forget, you still need to find this angle here, which is the angle that the weight makes with the radial. Okay, and we can find this out by what theta is. All right, bear with me, guys. So first step, just get all your basic stuff. Okay, the next step is we have an undefined path, the circular path, so we need to get psi. Okay, from psi, break it down to get its complementary angle, or you know, it's I don't know if that's technically the name complementary angle, but you know what I mean. 90 minus psi, and you can fully describe what this total angle is. Now, the way it's actually simpler than you think, right? We have theta equals 2 radians, right? So we have to convert that to degrees. So we have 2 radians. How do we convert to degrees? Easy. We just multiply by 180 divided by pi. Okay. And we have an angle of 114.59. So let's just say 0.6. Okay. So I'm going to erase these over here. Okay. So that this vector that I just drew is the weight, right? Theta is equal to 114.6. Okay. Now, let's see. So 114.6. Let's find. Sorry with the colors. I chose a terrible color here. So let's find what this angle is. Right, so that's 180 minus 114.6. So this angle is 65.4. Okay. Okay, so that's 65.4, which then leaves us with you know, we have this triangle here. Okay, I'm kind of drawing it out. So we have this triangle where one of the angles is 65.4. We know that this is 90. Okay, so what is this angle here? Okay, and this is the angle that we're interested in because this is the angle that the weight makes with the radial axis. Okay, and I don't know which Greek letter shall we use for this. Man, psi is usually my favorite one. Let's call it delta. Okay, that angle delta is just going to be 180 minus 65.4 minus 90, right? Because we know that the internal angles of a triangle have to add up to 180. So 24.6 degrees. Okay. So now that we have that angle, so let's go back to that drawing that I was doing in the bottom left over here. So this angle theta delta is 24.6. Very close to the 26.6, right? But it's not. And then from here, now we can do the summation of the forces, of the two force equations. We can say, okay, what are all the forces that are acting? Let's do the radial direction. What are all the forces that are acting on the radial direction? Okay. And oops. Right, and then what are all the forces that are acting in the theta direction? Okay, I guess one thing I forgot to do is get the acceleration terms. So AR, okay, is R double dot minus R theta dot squared. Okay, if we evaluate all these, we should end up getting, what's that, 0.5 times theta, that's just 1. 0.5 times theta dot, that's just 1. And then this is 0.5. They made it very easy for us. And this is what you should get. And then a theta, r theta double dot plus 2r dot theta dots equals 5 meters per second squared. Okay. Whew. It's a lot. There's a lot. That's why I wanted to spend a little extra time with these problems. All right. So let's work the forces in the radial direction, like I said. This will be, let's see, minus the weight, okay, cosine 24.6. Notice how I converted everything to this angle to degrees, and when I plug everything into my cosines here, I'm going to be doing, make sure your calculator is in degree mode, okay. So minus weight times cosine 24.6 minus the normal that I'm looking for times cosine 26.6. Okay. Am I missing other forces? No, I'm not. Yeah, so we should have just those two equals to the mass. The mass of this is 0.5. And then we're in the radial direction, so minus 3.5. Okay. So here, this first term will be, let's see, 24.6. This is minus 4.46 minus 0.89 times the normal that I'm looking for equals minus 1.75. All right, let's just do all the algebra here, and we should get 4.46 3.04 minus 3.04 pounds. Okay. All right, and that is the normal that is acting on the cylinder, right? So cylinder C, all right. And then if we find n theta, we can approach it the same exact way. So let's go back a second. So this will be determine the force of the rod on the cylinder and the normal force of the slot. So this is the normal force of the slot on the cylinder. Okay, so slot on cylinder. All right, and then let's find the normal force on the rod on the cylinder by the forked rod. So we're going to have n theta, right? These are all the forces in the theta direction. N theta plus the weight sine 24.6. Okay, remember the theta component of the weight. And what else do we have? Plus this n sine 26.6 equals 0.5 times a theta, which is 5. All right, so all I'm going to do is just plug this into my calculator, and we're going to see. Let's see what we get. So this is 2.04. This is minus 1.36. Sorry about this little squiggly I just did. Alright, and .5 on this side. What else? What else? And then let's isolate n theta. 2.5 plus 1.36 minus 2.04. And then we get 0.82 pounds. Oh, sorry. Why pounds? Why am I doing pounds? These are newtons. You know, when I was doing all my classes, I had the book, the dynamics book, in SI coordinate system, all in SI units, because I bought the International Student Edition, which was nice because I didn't have to worry about pounds and slugs and crap like that. But yes, so you know, this book kind of throws you back and forth through pounds, so the English system and the SI system. But that's what we get. So this is the rod on cylinder. Okay. So feel free to, you know, jump to the next problem, but just to summarize, this is how we began all our problems so far. Let's absorb all the information they give us, write it down, do the first two time derivatives, get r dot, r double dot, theta double dot, calculate our accelerations, right? And now ask yourself, is my particle on a defined circular path or an undefined circular path, right? If it's an undefined circular path, like the one we're given, we have to first determine where, you know, kind of draw the tangent and get the angle between the tangent and the corresponding coordinate system that we use, which is the r theta coordinate system. If your particle is on a perfect circle or something like that, then we don't have to do that because we know theta is gonna be aligning right with the tangent, right? So that's why if you think back on the problems that we've done in the past and we haven't had to do that, it's because they're like on a defined circular path. Okay. But yeah, so once you're there, once you get the angles, try to make your drawing bigger. That way you can kind of give it space so you can visually see where the angles are. Kind of like what I did down here. If I wasn't limited with space here, I probably would have just done it a lot bigger. And also, ideally, I would love to have this picture blown up, made huge, so I can just draw the forces on the diagram itself, which is easier to see. But yeah, so once you have your forces down, get the angles, you know, you have to, once you have your forces, you have to make sure you break them down into the corresponding components, its components, which is r and theta components. And then from there on, it's just Newton's second law, apply equations of motion, and then we're home free. Thanks for your time, guys. Really appreciate it. Like I mentioned before, these are, you know, this is slot on cylinder. There's the force here. The rod on cylinder. This is the normal force exerted there. And that's it. Hope this video helped. Appreciate your guys' time and attention. Don't forget to like and comment down below if you have any questions, and subscribe if you find this channel useful. Thanks, guys. Appreciate it.